this video, we're going to go ahead and go a little further into integer exponents. We've already covered the concept of what an integer exponent actually is, and we also went through and did some examples kind of simplifying expressions involving negative exponents and positive exponents, that type of thing. So you should be pretty well versed with that. At this point, we're going to go ahead and look at some polynomials and factor them by factoring out negative exponent expressions or factors with negative exponents, or we're going to distribute into a polynomial a factor having a negative exponent. So the prerequisites here is that you have to know what an integer exponent is and how to use them. You got to know a little bit about polynomials. It's assumed that you've already done a lot of work with those and that you know how to distribute into a polynomial and how to factor out of a polynomial. We'll start with a simple example. We're going to expand this expression, and when I say expand the expression, there's a lot of different ways that could be said. Some people might say write the product as a sum of powers. Other people might just simply say multiply. There's a lot of other ways to write this out. I usually just say expand, but multiply works just as nicely. They all mean kind of the same thing. Other people, by the way, might say distribute. Distribute works as well, so maybe I'll write that in as well, distribute. Now recall with distribution, you take the object or the factor on the outside and you distribute it to each object that's on the inside of the parentheses. Remember, every term on the inside of the parentheses gets this x to the negative 1 attached to it. This is no different than what you learned way back in pre-algebra or your initial algebra course. So you get something like x to the negative 1 times x to the second power minus x to the negative 1 times 3x plus x to the negative 1 times 2. And then you can clean this up. X to the negative 1 times x squared, you would add those exponents. Now, I say add those exponents, and actually in the last lecture, what I told you to do is if you had x to the negative 1 times x to the second power is to rewrite that negative 1 as a fraction 1 over x to the first. Well, you could do that here. That's absolutely fine. You get this x squared over x to the first, and you see, let's see, who wins and by how much? The top wins by 1. So this expression here, x to the negative 1 times x squared, becomes x to the first. But with exponents, you have the option of doing a lot of different methods for performing your operations. You could have instead said, listen, I know that we have this theorem that says if I have the same bases with different exponents and they're multiplying each other, I can add their exponents, a negative 1 plus 2, which is going to be x to the first. You can see that this idea of adding the exponents is really fast in this case. And this is what I think presents a difficulty for a lot of students, is that once they're given the option of choice of how to do things, they start to kind of get a little freaked out. So don't get too freaked out though. You can do this. Alright, so the first term becomes x. The second term here, I'm going to use commutative property of multiplication. In other words, I'm going to move around some multiplication here. I'm going to move that 3 up front, x and negative 1, x. And I'm going to also use a commutative property of multiplication in the last term. So it's 2 times x to the negative 1. To be honest with you, I am not a huge fan of the language of mathematics because a lot of people understand that they can move any number in a multiplication around. They don't understand or don't know the definition of it, which is absolutely fine. But you might have an instructor that requires you to know that that was the commutative property of multiplication. Alright, anyhow, let's simplify this out. X to the negative 1 times x, well, let's see, x to the negative 1 times x, which is x to the first. I'll just add their exponents. I get x to the 0th, and if you recall, x to the 0th, or any number to the 0th, is just 1. And we're going to go ahead and assume that x here is non-zero. So we'll assume that this is just 1. Plus 2, x to the negative 1 is another way of writing 1 over x to the 1. So this will be x minus 3 plus 2 over x. And again, let me make a little note here. Some instructors don't mind if you write this last term as 2 times x to the negative 1. Other instructors prefer that you write all your powers with positive exponents. If you're asked to write powers with positive exponents, please drop that x downstairs like I did. But if you're not told to do it, it's perfectly fine to leave the last term as 2x to the negative 1. And in fact, in more advanced mathematics, you generally do that. Having gone through one example, let's just try another one here. I'm going to go ahead and distribute 2u to the negative 3 times the quantity, negative 2u to the third minus u to the second plus 3u. And remember, distribution is just multiplication. You just take this initial factor here, 2u to the negative third, and you distribute it to each of the objects inside the parentheses. So each of the terms in here. I'm going to speed up the distribution a little bit. I mean, I'll still take my time with it, but not as long as I took last time. This is 2u to the negative third times negative 2u to the third minus 2u to the third, u to the negative third, times u squared plus 2u to the negative third times 3u. And again, I'm going to assume I want to write my answer with positive exponents. However, your instructor might be okay with you writing your exponents as negatives. 2 times the negative 2 gives me a negative 4. U to the negative third times u to the positive third becomes u to the 0, or in other words, 1. Well, I'm not going to write the, well, maybe I will just to show you that that turns into a 1. Minus, well, just 2, because that's 2 times the coefficient of 1 is just 2. U to the negative third times u squared is going to be u to the negative 1 plus 6. U to the negative third times u is u to the negative 2. Now, like I said, your instructor might want you to stop here, except for maybe writing that 1 or that negative 4 is just a negative 4. But if you have an instructor that prefers you to write things with positive exponents, then here we have this. Remember, u to the negative 1 means 1 over u plus 6 times u to the negative 2 is just 1 over u to the positive 2. And that's it. That's our distribution. There's something I want you to take note of here. When you distribute, you are literally multiplying in to an expression or a polynomial or some type of algebraic expression. However, when you factor, you're dividing. Factoring is the opposite of distribution. So factoring, with distribution you multiplied. Factoring, you're going to divide. So if they ask me to factor out something from some type of expression, that means divide that something out. So they're asking me to factor out a 4x to the negative 2. Well, what I had originally in this first spot was a 4x squared, but I'm dividing out a 4x to the negative 2. So let's see what that term becomes. Equals, well, the 4 over 4 cancels and becomes 1 over 1, which is just 1. And x squared over x to the negative 2, well, let's see. The x to the negative 2, I can take the negative off the exponent and pop that up top. So it becomes an x to the positive 2 up top, and then combine those two to become x to the fourth. So this first term is now x to the fourth because I divided out a 4x to the negative second. Plus, the second term was a 16x to the negative second, and I'm dividing out a 4x to the negative second. And here's where you're going to use a little bit of just intelligence that you've built up over the years, or actually knowledge, not intelligence. X to the negative 2 over x to the negative 2. Those are both the same picture, so they cancel nicely. That's just 1 over 1. And then 4 happens to go to 16 4 times. So this is going to reduce down to just the number 4. Okay. So again, those x to the negative 2 over x to the negative 2, those two factors canceled. They just disappeared. I didn't have to do any mathematics. They just cancel out. and then 4 went into 16 4 times. So this is the factored form. We're done. Check. We're okay. Now, the question is, how would we have known to factor out 4x to the negative 2? Well, let's go ahead and just take a simple example from the past. Somebody comes along and says, hey, could you please factor this, in this case, a polynomial? What you're looking for is the greatest common factor. Or I usually don't even say that. I just say, hey, look, what do all these terms have in common? As far as coefficients, all their coefficients are divisible by 3. So I'm looking for the largest number that divides into each of those coefficients, and it's not 6, right? Because 6 doesn't go into 3 nicely, and 6 doesn't go into this other 3 very nicely. But 3 happens to go into all of these numbers very nicely. So I can factor out a 3. And then you look at the variable factors, and you say, well, okay, what can divide nicely, or what do they all share as far as variable factors? Well, x, and then is it an x squared? Is it an x? Is it an x cubed? Well, if it were an x squared, that means that this first term would have to have at least an x and an x to borrow, which it does. The second term would have to have at least an x times an x to borrow, which it does because it has an x squared. And this last term would have to have both an x and another x to borrow, but it doesn't. So an x squared would not be a good choice, nor would an x cubed, because again, this last term does not have enough power to factor out an x cubed. So only an x to the first. So when you factor that out, again, you had a 3x cubed here, but you're factoring out a 3x. When you do the division, the 3's cancel, x goes into x cubed, x squared times. Minus, we had a 6x squared, we're dividing out 3x, 3 goes into 6 twice, x goes into x squared, x times. And then finally, plus, we had a 3x, and we're dividing off 3x. Well, those cancel and become the number 1. Now, this is an extended example in that when you're done factoring, by the way, you should always rinse and repeat. In other words, you should just check and make sure, can I factor this resulting trinomial? Actually, you can. It's x minus 1 times x minus 1. It's one of those trinomials that factors further. Since this is a prerequisite for this section, I'm assuming you know how to do that. But the thing I want you to notice is the variable factor that we took out was not the highest power of x. It wasn't the middle power of x. It was the lowest power. It was the lowest powered occurrence. Oops, I was going to spell that wrong. So it's the lowest power occurrence of the common factor. So let's go ahead and carry this into another example, and this time with negative exponents, and see if we can do a correlation here. So let's go ahead and factor 3a to the negative third minus 3a plus a cubed. The first question you should ask is there a number that will divide easily into the coefficients? The only number that divides into each of those coefficients is the number 1, so they really don't have a common factor except for 1. But then you ask yourself, do they have a common variable factor? Which they do. It's an a. But what's the lowest powered occurrence? Just like in this previous example, I said, what's the lowest powered occurrence of x? The factor x here, and it was x to the first, so we factored that out. In this example, the lowest powered occurrence is not 1, it's not 3, actually negative 3 is lower than each of those, so negative 3. A to the negative 3 is what we're going to factor out. Now remember, factoring is division. So we had a 3a to the negative third here, but we're dividing out a to the negative third. Don't do the math. Just notice that a to the negative third is the same picture as this picture, so they cancel nicely, and you're just left with 3 in that position. Minus. Now, what we had here was a 3a to the first. We're dividing off, again, an a to the negative third. That'll equal, let's see, we have 3a to the first upstairs. Downstairs, I'm going to rip off that negative and pop that a to the third upstairs. And you see a's have the same base, so I'm just going to add their powers now. That's 3a to the fourth. So this is 3a a to the fourth. And finally, plus, and in this spot we had an a to the third, but we're dividing out an a to the negative third. Again, I will rip the negative off that denominator and pop that third upstairs. And now that they have the same base and they're both in this numerator, I can add up their coefficients, or their exponents. That'll become a to the sixth. Now this is beautiful, but let me just make sure that this doesn't factor any further by writing this, at least the polynomial on the inside of the parentheses, in decreasing power order. So a to the sixth minus 3a to the fourth plus 3. Well, this is not quadratic, nor is it quadratic-like, so this will not factor. This is as good as it gets. But it's good to always check that in the end to see if this trinomial will factor. But it's not like an a squared and an a, or an a to the eighth and an a to the fourth. This is just some random powers. But for this to be possible to factor, that would have to be double the power of that middle term. Okay, so that's how you make the decision on what to factor out. Let's try just one more example here. Sometimes you're given some type of expression where the powers are not given to you as negative exponents yet. In order to factor, you really should rewrite this where the exponents have powers that are negative. So in other words, do the opposite of what we've been doing. Normally we've been taking negative exponents, ripping off the negative, and popping things upstairs or downstairs. In this case, you can change a positive exponent into a negative exponent by, again, swapping its position. So I could throw a negative on this exponent here as long as I write that u upstairs. And I can write a negative on this third term, the exponent of the denominator, the third term, by moving this variable factor upstairs and throwing a negative exponent on there. Okay. So now we can ask ourselves, how are we going to factor this? Well, let's see. You first start by asking, what do all of these coefficients have in common? It looks to me, oh, you know what actually I'm going to do? Well, it doesn't matter. It looks to me like they're all divisible by 2. I was going to mention to write this in decreasing power order, but it actually already is in decreasing power order. If you think about it, this first term is of 0 degree, this is negative first degree, this is negative second degree. So that is decreasing power order. So if it is in decreasing power order, actually, we don't just factor off a 2. Generally, on your lead term, you factor off, if it's negative, the negative as well. So if this highest power term, which is a 0 degree term versus negative 1 versus negative 2, since it's negative, we'll factor off the negative as well. So I'm going to factor out a negative 2. And then you look through the variables and you ask yourself, what do they have in common? Well, if you look at this one doesn't really have a u, but you could say it does have a u to the 0th, doesn't it? Now they all have u's. So sometimes you can sneak in a variable. Say, well, they all have u's and the lowest powered occurrence is negative 2. Remember, going back 2 examples ago, we said we would take off the lowest powered occurrence here of x, and that would happen to be x to the first. In this example, the lowest powered occurrence, we kind of threw in there the u to the 0th so that they all had u in common, and then the lowest powered occurrence is u to the negative 2. Let's see what happens when we factor off a negative 2 u to the negative 2. In this first position, we had a negative 4 u to the 0th, and we're factoring out a negative 2 u to the negative 2. Well, negative 4 over negative 2 is just a positive 2. And then u to the negative 2, I'm going to rip off the negative and pop that upstairs to become a u to the second. And now I will add these coefficients because they're the same base, and they're multiplying. That's u to the second power. So this is 2u to the second power. In this second position, I had, well, a negative 2u to the negative 1, and I'm factoring out a negative 2u to the negative 2. You see the negative 2's will cancel, so I'll have just, well, actually, and then let me rewrite, in the numerator, I'll rip off the negative off that exponent and drop it downstairs so it becomes u to the first. In the denominator, I'll rip off the negative off that exponent and pop the u to the second upstairs. U to the 2 over u to the 1, who wins and by how much? The top wins by 1. So this is, and notice it's positive. No, I didn't write the sign in here because when you're dividing by a negative, it's almost easier to just steal this entire negative 2 here and talk about that. So our answer is a positive u to the first. And then finally we had a positive 6 u to the negative second, and we're dividing out a negative 2 u to the negative second. Again, these pictures, u to the negative seconds, cancel nicely. And we have negative 2 dividing into positive 6, which is a negative 3. Now we have this wonderful trinomial. So this is equal to negative 2u to the negative second times 2u squared plus u minus 3. I just want to check really quickly to see if this factors this trinomial here. It's always a good idea to check. I'm going to use the guess and check form. I know two numbers that multiply to 2 will be 2 and 1, and then two numbers that multiply to 3 are either a 3 and a 1 or a 3 and a 1. And now you just ask yourself, is there any way to combine 6 and 1 to get to this middle coefficient of 1? No. So there's no possibility there. And then you ask yourself, is there any way to combine 2 and 3 to get to that coefficient of middle coefficient of 1? And the answer is yes. There actually is a way, so let's go ahead and do that. 2u with a 3 and a 1u with a 1. And let's see, we want to reach a positive 1u, so this will be a positive 3 minus 1. Okay. Or minus the 2. Yeah. Okay, so that's completely factored. And now you can kind of see there is a power in factoring here, a method to the madness, I guess you could say. The reason why is that we factor, if I haven't mentioned it in the past, I might have, is that you have fewer operations in general when you factor items. Notice that the original problem had 1, 2, 3 terms. That means I have at least, well, technically I have at least 2 mathematical operations to perform, but in reality you usually have a lot more than that. And in this case, if I were to let u be a number, I'd have to, first of all, I'd have to say, okay, let's start with the back term here. I would square that value of u, so that's 1. I'll keep a tally of operations. If I let u be a number, I'd have to square it, so that'd be 1 operation. Then I'd take that and divide it by 6, that's another operation. And then I'd skip over this middle term and say, okay, I need to divide that 2 by u as well, so that's another operation. And now I have those two numbers and I would add those together, so that's another operation. And then I have this negative 4 and I add that to that result. So I have 5 operations there. And it turns out that that's actually fewer operations than what, in this case, than what we would have done if we would have just factored it. But I still want to tally it up here. So with the factored form, let's say somebody gives us a value for u. In this first factor here, I'm just going to subtract 1 from it. So that's 1 operation. The second one, I'm going to multiply it by 2 and then add 3. So that's 3 operations. And I'm going to multiply those two things together. So that's 4 operations just to get this stuff done. Then I'm going to substitute that value of u in here and square it. So that's 5 operations. I'm going to take 2 and divide that by that 6 operations. Then I'm going to multiply those. It's actually 7 operations in this case. So it turns out factoring in this case is not the best route computationally, but in general, I just want to tell you that in general, it is actually much better to factor an expression, because computationally, when you do things in computers, having something factored or simplified like this, it really does save time, and time technically is equal to money. So just a little piece of advice there. So this is it for distribution and factoring using negative exponents.